How's it going? Welcome to Elasmocast. Today we have a really cool episode where we're going to be talking about some Devonian chondrichthyans. And we have a special guest, Sue Turner. How are you doing?
Pretty good. It's not so hot today, so I am sitting here talking to you and not dripping with the wonderful humidity of Queensland. I'm fine. And how are you?
I'm doing well. I'm excited to talk some early shark relatives. So
Yes.
before we get into the cool sciencey stuff, what's your background and what are your fields of interest within paleontology?
Yeah, I grew up in the middle of England. I was born in Birmingham, right in the middle, and I grew up a little bit further to the northwest in a place called Wolverhampton. And one day when I was about 7 or 8, I went to the local library and there I found a wonderful book called The Dinosaur Book by a splendid man called Edwin Colbert. You may have come across him. Ed Colbert was one of America's great dinosaur men. He worked at the American Museum of Natural History. And that book, when I opened it, had all these wonderful words in it, like vertebrate paleontology. And it told me about Mary Anning, a woman who'd found some of the earliest important fossils. So I learned all those words and I read about dinosaurs and I got hooked, like many children now. But this was back in the 50s. That was an idea that took me through. And eventually, when I got to university in 1964 to Reading in southern England, I managed to have just the right person as my teacher, a man called Lambert Beverly Halstead, originally called Tarlo. And he became my teacher for geology, and I specialized in vertebrate paleontology. And when I graduated, I stayed on to start a PhD program with him. He had given me a topic on a bed of rock called the Ludlow Bone Bed, which you might have heard of. It's a special bed of rock, about 6 inches, 10 centimeters maximum, that goes all the way from the middle of England all the way down to South Wales, one single bed of rock. And it's absolutely full of fish scales. So millimeter-sized fish scales, millimeter cubes. And these fish scales, which I had to learn what they were, most of them were the scales of jawless fishes called thelodonts. But there were also scales of acanthodians and fin spines of acanthodians, the little jawed fish that have fin spines on all their fins, and a few other things as well. But mostly the Ludlow bone bed was full of thelodont scales. And in Britain, in the Geological Survey, for 200 years nearly, had used this bed as the division between the Silurian rocks in Britain and the Devonian ones. So that became part of my project, to understand these fishes and to figure out the stratigraphy and what these fish, what this bed of rock meant. And it was a very exciting project that took me to Shropshire in the Welsh borderlands and Herefordshire. And I worked on those thelodont scales and I identified them. And that was how I got into the beginnings of vertebrate paleontology. There were a few little remains that might have been shark-like, but at that stage, we didn't really know very much about those. I didn't really start to learn much about sharks and to actually go out and find them till I came to live in Australia. I spent my first 9, 10 years in Britain working in a museum in the north of England that introduced me to carboniferous coal measure vertebrates, fish, sharks, and tetrapods, four-legged amphibians. But then I came to live in Australia in 1980, and suddenly I had a whole continent available to me because nobody had ever looked at microfossil vertebrates to speak of in Australia. There had been wonderful finds, of course. Australia has some of the most important of the oldest fossils in the world and some of the most important of the youngest ones, especially our weird marsupial fauna. But I had all this chance to go out and look for rocks, and I would use my technique of stewing them up in acetic acid, which is a time-honored technique. And also I learned to use the microwave to break down more difficult rocks like sandstones and shales so that I could look for the fossils in them. And suddenly I began to find sharks, shark teeth especially. And the first ones I described from Australia were a weird lot of teeth that have 3 little hooks, which I originally called harpago. Sadly, that name was taken, very sad. But they look like little grappling hooks. And eventually this became known as Thrinacodes. They'd already been described in America. And eventually I came to look in America in the museums, and we found the original teeth that had been described in the 19th century. Those teeth took me to look for other shark remains and brought me into the whole field of fossil Paleozoic chondrichthyans, which I've been doing more or less ever since.
Awesome.
So anything else? When I went to the museum, of course, yes, when I left my job in England and came to Australia, I was very kindly invited to become a member of the Queensland Museum in Brisbane. And that's where I've worked ever since. They didn't have a job as such, so I became what was called an honorary research fellow, which means essentially, like many women scientists, I live on soft money. And a lot of men as well do that now because jobs are not easy to get. But when you become a vertebrate paleontologist, when you perhaps start a PhD, usually the man who's your teacher or woman will give you what we call the talk. And they say to you, as my supervisor did to me, Bev Halstead, he said, you will never get a job, you will never be rich, and you must be mad. And if you can accept those 3 things, then you can study vertebrate paleontology. So it's the very lucky ones who get a job. I don't know many vertebrate paleontologists that get ever so rich, at least not from vertebrate paleontology. And of course, we all are a little bit mad to do what we do, going out, digging up the rocks and looking for fossils. It's not exactly a normal thing to do.
Yeah.
Anyway, so I've been now in Australia for 45 years, and I have to say it's been a very good place to do science, but not a place to get a job.
Yeah, not many jobs in general worldwide for vert paleo, unfortunately.
No, sadly not.
Yeah. So the main chondrichthyan that we're going to be talking about today is one that you've worked on extensively, and that is Doliodus.
Mm-hmm.
So Doliodus latispinosus, which was previously Doliodus problematicus. This was an early Devonian chondrichthyan, and let's talk about the history of Doliodus and I guess like of description and things like that.
Well, I'll tell you about how I came across it. When I had found these Thrinacodes teeth in Australia, they were late Devonian to early Carboniferous. And I went to America to go and look in all the museums to see the older collections that had been described in the 19th century. And one of the museums I went to was the Museum of Comparative Zoology at Harvard University in Cambridge. And there I found in a drawer, I pulled this drawer out, and there was a tooth that was really weird. And the label said, Xenacanthus problematicus. And there was this tooth, rather like Thrinacodes, but it didn't have 3 cusps. It had 2 cusps, 2 big ones and little ones in between. But this fascinating, long, apparent root, just one tooth, started my interest in what we eventually called, as you said, Doliodus latispinosus. I looked up all I could about those teeth and learned a great deal and started to see if we had anything like them in Australia, which brought us to other sorts of shark teeth. But it wasn't until much later, in the late 90s and the early 2000s, that we actually found an answer to those isolated teeth. And that was with the discovery of the first part of the fossil that we later described as Doliodus problematicus. And that was the most astonishing beast, as you know.
Yeah. And let's talk about what makes Doliodus problematic. Like
Well,
why was this thing such a big
yeah,
discovery?
the reason it was problematic because those teeth were problematic, and that's why that one tooth at Harvard with the name problematicus, because they were only known from teeth in the 19th century. And from Harvard, I went to the other museum that had the big collection that had been described by Hussakoff and Bryant, Buffalo Museum of Natural History. And again, they didn't know what to do with those teeth. They were rather like xenocanth teeth. Those are the sharks that mostly are in the Carboniferous and found all over the world pretty well in coal measures, with two big separate cusps on the teeth, and then one, two, or three little ones in between. So it seemed completely out of place because the Xenocanthus problematicus teeth were in the lower Devonian, but all the other xenocanths were in the Carboniferous. So a good almost 100 million years difference in time. So that made the thing special. And when the actual specimen was found with those teeth in place, that was like a eureka moment. And then on top of that, the specimen that was found in the northern New Brunswick had pectoral fin spines. And that was totally unexpected for a shark. And that's what made it very, very special.
Yeah.
So
And
go on.
so I was going to say, so talking about the fin spines, what makes that such a unique feature with Doliodus and such an unexpected feature?
Well, we'd known fin spines, of course, like myself working on the Ludlow bone bed, which is sort of the top of the Silurian. It's got lots of little fin spines in, but they belong to acanthodians. And we knew a great deal about acanthodians from the early 1800s onwards, particularly in Britain. They're found in the Welsh borderlands, they're found in Scotland. Little tiny fishes, maybe only a few millimeters long, up to about 10, 20 centimeters, 30 centimeters. Acanthodians, we knew, went all the way through to the Permian, then they became extinct. And they had little fin spines all over their body on the fins. But they didn't have shark-like teeth. They only had little prong-like teeth. So they were not true sharks. In the early literature, you'll hear them called or see them written as spiny sharks. That was the other name for acanthodians. And they were cartilaginous, but people were not happy about putting them into the chondrichthyans with the other real sharks, if you like. So when Doliodus was found, and we could tell it had shark-like teeth, and from my work on the Buffalo Museum collection, we knew that the teeth that were called Xenocanthus and later Doliodus were rotating teeth, classically like a shark, where you know the shark teeth grow and they rotate out, and as they come to the front, they drop out as the shark bites something. And that's what we could see in Doliodus. So we knew it wasn't, that it was a shark, if you like, based on that alone. And then when we found the complete specimen in northern New Brunswick, my colleague Randy Miller and I took the specimen to show some geologists in the survey, and we were out in the weak Canadian sunshine, and we turned the specimen over, and we could see the outline of the brain case. So that was what another eureka moment, that Doliodus had a big brain case and made with the prismatic cartilage that we see only in sharks. So that made it again different from acanthodians as such.
Yeah, it's really interesting when we look at acanthodians, because we have Doliodus here, which has these shark-like features, but also these early acanthodian traits. But then, so that indicates that we have acanthodians as a paraphyletic group that goes into the, I guess, the crown chondrichthyan group. But then you also have acanthodians that still have that like acanthodian plan that go all the way into the Permian.
Into the Permian, yes. And so, again, what is paraphyletic, what is not? Maybe it's the chondrichthyans that are paraphyletic. We have lots of different types of chondrichthyans. At the moment, my colleague Carol Burrow and I are looking at chimeriforms, chimeras, and looking at the fins that they have and the interesting frontal claspers and so on. I mean, again, sharks typically have claspers for reproduction, at least not all the way back in time, but we probably have them now at least into the Devonian. So that was another trait that most sharks have. But chimeras, holocephalans, they're all a little bit different. So again, what really is a true phyletic relationship and what is parallelism? We're still really throwing all these things up into the mix, I think, especially as we go further back in time. And both Carol and myself have worked a lot on the scales. We found scales of sharks and acanthodians all the way back. Our colleague in Australia, Gavin Young, has found shark-like scales in the Ordovician in Australia, and others in different parts of the world. So it's very fascinating. I gave a talk many years ago at a meeting in Australia to say, well, sharks really for the first 40 million years or so, they don't have any teeth. They're only known from their scales. So are we right in saying these are really sharks? We're still up in the air, as I say. But Doliodus was really good when we found that specimen, that complete specimen, well, articulated specimen. Sadly, we're still missing the tail end. But we had the teeth that were shark-like. We had the brain case and the prismatic cartilage. And we had all the indications that this was a shark rather than an acanthodian.
Mm-hmm. And what I found really cool too was the scans that they did after the initial description of that specimen, and that there's even more spines than what we thought on it.
Yes, and we're still, I think, still arguing about what the spines at the back are, little pelvic spines, or are there claspers? We're still not totally sure. We do need more material, but we have the two lovely pieces that we managed to put together with the brain case in 3 dimensions. And the scales, I haven't actually written all I know about the Doliodus scales yet, but it's got a beautiful suite of scales with different types in different areas. Some around the eye are different, some in the branchial regions are different, and some of those scales in the branchial region really mirror some of those in the teeth as well. And a lovely set of teeth, of course, that change as they go around the jawline to the end of the mandible and so on, the maxilla. So when we started looking at the scales of Doliodus, the things that they reminded me of especially were Antarctilamna, our shark from Australia and Antarctica, in the slightly younger rocks in the Middle Devonian. So that was fascinating. And that group of sharks have rather complex scales, whereas other sharks, as we know, even going way back in time in the Silurian, have very simple placoid scales. That is a single pocket where they formed, and they're essentially like our teeth, as our teeth form in the same way. So even from the beginning, we have two different groups that have different sorts of scales. There are occasionally fossil sharks that seem to have both sorts of scales on their body. So it's a bit complicated, and we still don't know which of these types came first, although logically you would think that the simple placoid shark scales came before the more complex ones that are more like acanthodian scales. All these problems we still have to work on. Something for you to do. Was Jeff McGovern, who picked up this key fossil that we worked on. And then 6 months later, Richard Cloutier found the second part of the same fossil. But we didn't know that until I went to work in Canada in 2002. And we went to visit Richard to collect that specimen. And then we put the two together. And so we then recognized that we had this wonderful three-dimensional brain case. That was really one of the special times, I have to say. Yeah.
Yeah.
Yes.
It's an incredible fossil.
The sad part is that we haven't yet found any more. And lots of people now have scoured that little piece of coastline. It's not the greatest place to work because there's an enormous factory thing nearby pumping out sludge and all sorts of things onto the coastline. Mm-hmm. But there's plenty of rock. And there is a special bed where the isolated teeth came from that were first found by the wonderful collector, Mr. Jex. That bed is at the base of the section. Now, when I went and we walked along the section, you can see how this bed squeezes into the rocks below it. So it must have been a very soft rock and probably killed those animals, the sharks, moved the plants in a very fast movement. I interpreted that as a possible tsunami event where the mud was, or something like a landslide, where it just went down very quickly and scoured the whole surface and killed all the things in front of it. I think some of the geologists and up there had got a slightly different interpretation. But no matter, this bed is full of the teeth of Doliodus and the other shark that we only know again from its teeth, Protodus, called after Mr. Jexi, and possible spines that belong to that too. So we still have another mystery shark there that we don't know a great deal about.
Mm-hmm. So what do we currently think as far as the phylogeny of Doliodus? Like, what's the most recent interpretations of that?
I think, it's being used in a lot of phylogenetic analyses and is placed at the stem chondrichthyes level, again, with next to sharks like Antarctilamna and, Doliodus, as we talked about earlier, that may or may not be exactly the same thing. So it's, of course, a very important fossil used in these cladistic analyses. With the acanthodians, not quite at that level, if you like. I was the one that changed the Omelodonti D, and my dear colleague, Michael Ginter, has done a great deal of work on those particular ones that are a bit younger. The teeth are very similar, but yes, they may not be exactly the same. It could be a basal omelodont. Some people have said that. Or it could be, as I say, like Antarctilamna, which to me, it's much more close to that. But who knows? Again, we don't have enough information as yet. And we always need new fossils to help us understand these things. So I'll leave it up to you to decide.
And let's talk a little bit too about the age of Doliodus as well as what was around at that time.
Mm-hmm. Yeah, well, I think the general, based on all the various different evidences from well, the fish themselves, the plants, the geochemistry, is putting it as early Devonian, around 410 million. There were, of course, plants on the land by then. So Doliodus was probably living in the shallow water alongside the other one I mentioned, Protodus. We don't know how that looked like at all. But the land would have been covered with the plants like Cooksonia and other small, a bit like lycopods and so on. And we know that near where Doliodus died, there was big volcanoes going off at the time. If you think of the volcanic rocks of Montreal and elsewhere in Quebec, so there were eruptions happening, ash in the air, and so on. It would have been quite a dramatic landscape, not unlike, say, the Indonesian islands here to the north of Australia. And Doliodus, along with acanthodians that were also there, climatius type of acanthodians, were living in the same seas. What were they eating? With Doliodus's teeth, they were probably catching small invertebrates. There were also, of course, we know from Randy Miller's work, some very big eurypterids, the enormous sea scorpions, which we did suggest could have been one of the predators on little sharks like Doliodus, which is nice to think about. We had one specimen where we had a very big eurypterid claw sitting very near a tooth of Doliodus. I mean, it's nice to imagine, but we don't have any real proof, of course, of whether the two interacted.
So I don't think we talked about how large Doliodus was, because it was a pretty small chondrichthyan.
Yeah, I mean, the specimen with the brain case was about this big, and the articulated specimen we had was 20, 30 centimeters. So based on the sort of classic formula for fish, the size of the head, the body, and then the tail, you would probably looking at a shark about half a meter to 2/3 of a meter long. So not a large shark, but based on what the teeth looked like, we presume it was an adult, not a baby. And of course, like modern sharks, it's possible that some of the younger, the baby sharks, the juveniles, were represented in that older bed where we get lots and lots of isolated teeth. And some of the teeth are very small. So they could be juvenile teeth, or they could be the teeth from the very sides of the jaw, where the teeth get smaller as they go along the tooth rows. Again, we need more specimens. You have to go out. I'm too old now for field work. You have to go and do it, you young folk.
Yeah, unfortunately, Canada is a little bit of a hike from here in Arizona, but it would be a fun trip.
But I mean, in theory, you can go and look anywhere in the Lower Devonian or the Late Silurian and hopefully pick up something useful. As we did, and Carol and I went and worked on this thing that was called Nostolepis scoticus originally. And there was one very nice specimen from Scotland and another specimen from the Welsh borderlands. So two quite separate areas. And that turned out to be the answer to a puzzle we'd had, because we had hundreds of thousands of scales called Nostolepis from all the work that had been done in the past century on all the bone beds across Europe. And into Canada and the USA and in Australia. We had hundreds of thousands of scales that we called Nostolepis. But then we realized we had an actual specimen. And when Carol and I looked at it, it was called something else at the time. It was called Protodus, after the one from New Brunswick. And we showed it to our colleague Jo Vergusen of Holland as well. And I think it was he who first said, oh, the scales look like Nostolepus. So we, again, when you start to put together the evidence, you can sometimes solve problems. And in that case, looking at the scales of that specimen made us realize that this was an animal with nostolepid scales. And finally, we realized that it was an acanthodian of quite a good substance. It had a brain case too, and it had little teeth. They were quite just simple prongy teeth, but it was a very useful discovery. We need more. Finding articulated or complete specimens is the hardest thing, whether you're, especially when you're dealing with sharks that are cartilaginous, mostly cartilaginous.
Yeah.
I mean, mostly I'm working on the older jawless fishes, the thelodonts. Now, thelodonts are fascinating because they are, again, they're cartilaginous animals, but they have, again, placoid scales, simple scales made of dentine with a bony base that we call aspidin. So there's no bone cells in it. But those scales, again, millimeter-sized scales, are exactly the same as those of modern sharks and of many of the sharks through time. So were those jawless thelodonts related to the later true sharks when jaws had developed in evolution and then teeth developed in evolution? As I said, in the first sharks, for the first 40 million years, we don't have any shark teeth. Maybe even longer than 40 million years now. So we have to derive sharks from somewhere. Did they come from thelodonts? We still don't know the answers.
It's feasible, especially when we look at, like you said before, chondrichthyans in like the oldest ones not having any teeth. If chondrichthyans have already derived from other fish by that time, other jawed fish, but then they evolved teeth later on, that means that teeth evolved independently in all these different lineages.
In different lineages, that's right. And I think there is certainly some evidence for that, because then we see the teeth in placoderms that are very strange and quite different. So the jawless fishes managed very, very well for 100 million years or more without any teeth. And we still have a few jawless fish around that still, 500 million years later, still going strong. They did it in a slightly different way. They created little horny things. And then we get into the whole topic of the dreaded conodonts, which I've worked on and don't believe they're anything to do with vertebrates, at least not true vertebrates. But fish do evolve strange structures. However, as I say, with those shark-like teeth that we see, shark-like scales that we see before the time, say, of Doliodus, and we have the simple placoid scales and we have more complex scales. So even from the beginning, it seems we're dealing with more than one type of shark. And so, yes, are sharks not a sort of natural group? We still have lots of questions to answer.
Yeah, there's still a lot that's left to learn in vertebrate paleontology. A lot of people kind of assume that just like everything is known already, that there's no advancements, but in reality, there's huge gaps of information, especially when we go back towards the stem of vertebrate evolution. There's a ton of gaps and holes and everything that need to be solved.
Yeah, and the origins of things. I mean, if we have Doliodus in the Lower Devonian, then we need to go a little bit back in time, a bit earlier in the Devonian, then the late Silurian, and see if we can pick up similar things. And it's that detective work, bed by bed, that we need. And it's not always done. Of course, it's much more exciting perhaps to go out and find a dinosaur. Enormous, great thing. So working on microfossils has its frustrations, I have to say, because they're not quite as sexy as dinosaurs or beautiful mammals or whatever. But we have to look back in time to realize the origins of these groups. The other one I think I mentioned to you, I'm working on the gyrocanths. Now, they've always been shoved into the acanthodians, but in fact, they're a lot more like sharks in many ways. And apart from the fact that they don't seem to have any teeth at all. And yet they got to enormous sizes, 3-4 meters long, with these enormous fin spines. But were they like modern catfish or like filter feeding in the rivers? Don't know. We still don't know enough. But where did they come from? We've got them back to the late Silurian, early Devonian in South America and in Europe. But we have to go further back in time.
I love looking at the stems of things. There's a lot of derived stuff is cool and all, but I think that the mysteries of life at the stem is really where things are interesting.
Yeah. And that's why I would encourage people to start looking in the Ordovician. We really need more answers from the Ordovician. I mean, we've had some good, exciting finds in the last decade or so, particularly from Oman. The colleagues in Birmingham and Australia worked on this new suite of fossils from Oman, where we have some of the earliest vertebrates, and also, of course, the classic Harding sandstone from the USA, where there are lots of fascinating things. But we really need to look through the Ordovician as much as we can and try and go even further, of course.
Yeah.
Nobody's really looked that much in the Cambrian yet.
So let's talk about another Devonian chondrichthyan, Mcmurdodus. So this is something that a lot of people talk about in the shark tooth community because there's like, I guess, a niche of shark tooth collectors that are obsessed with cow sharks and cow shark teeth. And then you have this this chondrichthyan whose teeth superficially resemble those in the Devonian. I personally agree with you that they look more like Echinorinus, bramble teeth. But nonetheless, it's been compared to both of those. And
of course, we've got 300 million years gap, if you like. So it seems a bit unlikely that they are related. So maybe it is purely an environmental thing, that the Mcmurdodus type teeth and now Masiodus, we made a new genus when John Long and colleagues found new material in Victoria. And we decided to call the Queensland one and the Victorian ones in this new genus for John Maisie in his honour. But those plus the Mcmurdodus ones from Antarctica have these rather interesting teeth. And that's, again, we still don't know a great deal about the shark itself, except, it was another smallish shark living in the shallow water in marine. So around the shores of Gondwana, we have to go and look for some more material. But where Mcmurdodus that we found from Queensland, that's really a very remote place. I've not actually been, but Carol Burrow, my dear colleague, went with Gavin Young, and I think John Long too. They went and collected more. It was, for me, when I first found that tooth, it was again another of these eureka moments, because when you find something and you just cannot, you've never seen anything like it before, it's really quite fascinating. That's one of the joys of looking down the microscope, because you know that you're looking at things that nobody's ever seen before. I was then able to link it to the one from Antarctica, which Gavin had worked on as well. And they weren't exactly the same, which is why we gave it a new species name. Mm-hmm. And then the new material that we've recently described from Victoria has at least given us some new ideas about how they relate to one another. Again, it's not easy to nip down to Antarctica to do more collecting. You have to really be a young, fit person and get the money to go all that way. So something else for you to think about.
And could you describe, for people that have never seen them before, what Mcmurdodus and Masiodus teeth look like?
Can I describe what they look like? Well, as you mentioned, cow sharks and bramble sharks. So they're rather long. They're not terribly big, again. They're really only millimeter size, the ones from Queensland. The Antarctic one is slightly bigger. And they have these rather triangular cusps on them that quite large, and then they reduce down in size towards the edge of the tooth. And that is a feature that's found in bramble sharks and some of the cow sharks, like Hexanthus and so
on. With Mcmurdodus, I do agree that it's probably a case of convergence, because when we look at the hexanchiforms, we don't have any definitive hexanchiforms until the early Jurassic, which is a huge gap. Yeah. I think a Japanese locality of a hexanchus tooth from the Permian, but I couldn't find any actual pictures of that, so I don't know how reliable it was.
I'd have to look. Mr. Goto was the Japanese man, Masatoshi Goto. He was a dentist by training, and he started looking for teeth when we were doing the UNESCO project. He did a lot of good work, but he didn't always illustrate, as you say. But there are also, as well, a lot of amateur paleontologists in Japan that write little short notes in local magazines. So again, yes, it would be good to do a lot more in Japan. Probably we would get some answers. And the same problem with Indonesia. We've got just a few little remains that an enormous continent that we know almost nothing about. I started the plan to go and look in Malaysia and in Korea, again, two places where almost no work has been done. So we really, if we want to fill these gaps, we have to go and look and start projects to look at beds one by one and see if we can find new remains.
For sure, yeah.
But yes, I think, yes, I'm pretty sure, like you, Mcmurdodus, which is really, at the moment, restricted to East Gondwana. Again, we must look outside of East Gondwana, maybe in China, which was closely related to Gondwana at that time, to see if we can find new evidence.
And is there anything else that we know of with, or at least that we think of with Mcmurdodus and its relatives like Masiodus, that would tell us a clear indication of where it sits phylogenetically? Because it's, as we said, it's unlikely that it's a true shark, like a cow shark or a bramble shark. But is there any indication of it being somewhere else or having some other relations?
Not really at the moment, until we find more articulated remains. Did it have a fin spine? We have no idea even really what the scales are. So it's like so many of the, ichthyoliths, ichthyodorolites, the scales, the fin spines. We don't really know where to put them until we find a complete specimen. Um, I mean, we don't have to, like the olden days when they used these terms. The older books had big sections on ichthyodorolites. We have slowly pinned down many of these sharks. Carol's done a good job with recognizing that some of the fin spines are placoderm and some are acanthodian and some are chondrichthyan. I was reading this morning about in Colin Patterson's work on chimeriforms. Another one we're interested in is Orocanthus, which again we know very little about, but maybe a holocephalon, a chimeriform, or is it, as some people said, related to gyrocanths? Again, these problems need to be solved, but we can only really solve them by finding complete specimens.
Mm-hmm.
We need everybody out there bashing the rocks.
If only Paleo had the money to pay us to go out and do that.
Yes. Well, I mean, this is where amateur paleontologists, the so-called citizen scientists, are so important and always have been right from the beginning. Mary Anning, Elizabeth Bennet, and all the others in the late 1700s through 1800s. They were not trained geologists. They were just out and enjoying themselves, or in Mary Anning's case, making a living out of it too. But we do need people on the ground. And some of the best people, of course, are children, because they're closer to the ground and they've got very good eyesight. So, we should employ our children more often in getting out there to look at the rocks.
Yeah, I do think that citizen scientists are extremely important, especially so like that's how I started, and
Uh-huh.
and a lot of these fossils, there's just not enough paleontologists to go out and find them, and then you
Mm-hmm.
have elements that degrade these fossils over time. So the same
Mm-hmm.
fossils that are outlying about now might be dust in 10 years or even
Absolutely. Yes.
so it's either the stuff goes just disappears or you have some people that are really passionate and find something. And a lot of these
Mm.
people might not have an interest in paleontology until they find that first shark tooth
That's
or
right.
that
That's right.
first bone.
I
And then
mean,
that,
like me, it took that book. Colbert's book leapt out at me from the shelf of the library. And then that was reinforced a couple of years later when I was at high school. We went on a field trip to North Wales and we were up the Great Orme, as it's called, which is a big carboniferous mountain. And I picked up my first fossil, which happened to be a bit of coral. So, I mean, those are the moments that lead you to your future, destiny. You have no idea what it's going to do. So yes, picking up your first fossil is a very important moment in life. I mean, not everybody has the chance to go on, and so, and certainly now, like in Australia, there are not many jobs. A lot of us are getting old, so we need young blood to come in and take our places and do that essential field work. So there you are. You've got a whole world to play with.
yeah, I'm
But
excited.
it would be nice if we could persuade some of the rich people of the world to be a little bit more generous with their money, and the obvious way then is to name a fossil after them. That's been done on several occasions.
Mm-hmm.
And one of the most important ones like that was Mr. Carnegie, who funded museums and libraries across the world, and he got a few named after him, because he funded putting up of skeletons and so on, fossil skeletons. So yes, maybe we should do a survey around the world of who are the richest people and see if they'd like to have a fossil name after them.
So one last question that I like to ask before we wrap up these podcasts is if there is one discovery that would be that you could make in your before like in your lifetime
Or I
you'd want to
die.
see like you'd want to see done more than like anything else,
Mm.
what would that discovery be?
Oh, really? There's lots of things. Well, it would be very nice to have a really complete Doliodus from tip of the snout to the end of the tail that we could see again in 3 dimensions. If we could turn it over and really see how it fits with many other things, that would be a really good one. Um, but yes, and then the other shark alongside it, Protodus, we know still so very little. Um, and this is the problem with sharks. I mean, they're all cartilaginous, so they don't preserve well. When I was young at university, we had Al Romer's wonderful vertebrate paleontology textbook. And in that, you read there were no sharks before the late Devonian. The Cleveland sharks from that area were beautifully preserved. And Mike Williams, who was at the museum up there, Cleveland Museum, he came up with an interpretation that somehow those sharks had died in an environment where it was almost like embalming fluid, that the water had literally embalmed them so that all the tissue was there. Now, that is a rare event, and it would be so nice if it happened more regularly in the fossil record so that we could find not just complete sharks, but complete agnathans for me. There are so few, complete thelodonts. We have none from Australia whatsoever. We have a lot of thelodonts, but we have no complete animals. So these are the sorts of things that a paleontologist like me prays for, if we pray at all.
I would definitely love to see a full Doliodus. That would be
Yes, yes,
that would be awesome.
that would be very nice. Mm.
Well, thank you so much, Sue, for joining. This was a great talk.
Good.
For those that are watching, please don't forget to like, comment, subscribe, do your thing so that you can support a Chondrichthyan Center channel because there's not very much out there for that.